Okay. Hi everyone. My name is Tianyang, and I'm from Buro Happold, and it's a global engineering consultancy, and we're also in collaboration with Birmingham City University, our academic supervisor. I'll try to be fast so everybody can go for their lunch just in time. My topic today is benchmarking deep learning approaches for AEC engineering drawing layout detection. A little bit of the background. So drawings still are the key kind of information carrier in the AEC industry. So the architects need to design the building by drawings. Also, engineers need to do their structure design or the other stuff. And in the construction side, they need their engineering drawings to really building to build a building to do construction. And in all this process, the manual information extraction is still the main approaches, and it is very time-consuming and important. And particularly in Buro Happold, we need to deal with some large-scale refurbishment project where we always get those kind of drawings from 60s, 70s, 70s from last century, and it is really hard because we really need to do manual query from tons of drawings. And also drawing information detection is very critical for downstream tasks like quality assurance, auditing, and even digital twins and BIM models. They all depend on the accurate drawing interpretation. And here we frame the three layers of information in the engineering drawings. So the first layer is the metadata layer. It's basically the information that is within the title block. So we will have the drawing number, the title number, the drawing number, the project number, like the project name, the drawing name, something like that. Then the second layer will be the layout. It's like a whole graphical kind of organization of the drawings. So we will have the title block down below, some notes and legends scattering around, and in the middle we will have the main drawing content, which is the main graphical representation of some details of the building. And so in our prior work, my lab manager Alessio presented in the EC3 conference last year. We kind of solved this problem of doing metadata extraction. So we used a FastRCN plus GPT-4 pipeline for the title block information extraction. And the result is quite well, and we validated on the real Buro Happold facade engineering projects. And coming to the layout detection, we do have some research gap, and that's why we're doing this thing. So the first gap is the AEC research targets. It basically targets on floor plan. So yeah, a lot of research I've seen, they've been doing floor plan layout analysis, and that's nothing related to our engineering drawing layout detection. They are basically doing kind of room detection or segmentation and detecting the walls, windows, and the door. But in this work, we're more kind of focusing on the whole drawing kind of organization. And also, I think why people are focusing on floor plan most is that the real engineering drawings is kind of not that publicly available. But we do have a lot of floor plan, like quite huge data set available on the internet. So the second gap is the document, general document AI versus engineering drawing documents. So we, doing the kind of lib review, we've spotted quite a lot of general document AI models in datasets. So some famous one like Layout LN, like Layout YOLO, and some very famous dataset like PubLayNet. They have kind of like 80,000 kind of public kind of general documents. So this is like an example of the general documents. But their general documents are mostly text dominant, and they're very standardized aspect ratios. So they're basically in the A4 paper. They have lower resolution compared to the AEC drawings, and they do have large-scale public data set and benchmarks available. But compared to our engineering drawings, it's basically line and symbol dominance. So you will see a lot of kind of graphical representation in a drawing, and they do have extreme aspect ratios and very high resolutions. If we render the kind of the A0, I guess, yeah. If we render the A0 engineering drawings in 300 dpi, you will get some figure like 14K pixels times like 10K pixels. And yeah, there's no existing AEC layout benchmark because we just don't have the public available dataset. So this is dataset we proposed. We kind of collect drawings from 10 real Happold projects, and we have 551 drawing sheets. We identified 9 layout categories, which is something like sections, details, plan, elevation, and we do have title blocks, notes, legends, and revision table, this kind of stuff. So overall, we have like over 2,000 instances. And in this work, we benchmarked 5 models spanning in different paradigms. So we do have the traditional 2-stage fast RCN, and also the YOLO V12, which is like a representative for 1 stage. We do have the latest detection transformer, the DETR, and we also tested some open source vision language models, and one general document, specifically the model doc layout YOLO, which is designed for general documents. And here is the basic result of it. As we can see, I think the RFD-TR, the detection transformer, outperforms the other models, but the Quen3 vision language model with the 8 billion parameters, it also performs well. It reaches the highest F1 score. For the fast singing and YOLO, you can see the difference not that big. The YOLO is like the fastest in the inference time. Yeah, that's basically all. And also you can see the doc layout YOLO, the model that is developed for the general documents, performs so badly in engineering drawings. And here is a bit category level results that review the distinct model strengths. So you can see, yeah, as before, the detection transformer dominates across all categories. So it basically achieves like the highest accuracy, like mean average position in basically every layouts, like in every categories. And doc layout YOLO, it shows extreme polarization. So like the title block, it's like a reasonable figure for it, right? And I think the main reason why is because, you know, the title block is basically text-centric. You will have the title block that is formed by text. But for the general arrangement section, I mean, it is really yeah, bad. It's like nearly 0. So you can see the general documents part are actively interfered with the AEC specific categories. So, and for the Quen3 video, at least the overall F1 score, as we shown on the last slides, and it also like demonstrate like, so we will have the legends. So if you look at the legends, like the mean average positions exactly 1. So it's really useful that the vision language model that can bring some kind of understanding even from the text, so you can get some context from the text of the drawing. So I guess it just have more information. So it has the privilege to read the text and understand what's going on in some specific area of the drawing. And here we also did an application study on the doc layout YOLO model. So the doc layout YOLO is basically built on the YOLO V10. So we train the YOLO V10 as well as the baseline, and they do have so the doc layout YOLO, they do have this kind of architecture, this kind of tailored module for general document. But you see, if we add up this kind of module that is tailored for the general documents, it performs the performance dropped by 5.8%. And if we train it on the doc layout, which is a kind of large-scale general document data set, you will see like 23% drops on the performance. So you will see there's kind of general documents like model cannot just be generalized onto engineering drawings field. And yeah, and here are some visual analysis of it. So this is some success case, and this is some failure case. Yeah, I'll try to be fast and skip this page. Some key takeaways. So first is the first benchmark data set. Sorry, but this is not publicly available. This is from Buro project. But we're really looking to some publicly available data sets. Yeah, so thanks for Sylvander. I mean, yeah, he find out some really good kind of historical drawing from America, and we also spot some the other works who use the governmental public projects from US as well. Yeah, if anyone is interested, just let me know. So second, the detection transformer is it's the best, and you will see the key domain interference. So the general document layout, pre-training, post-negativity transfer, and the dot layout YOLO just cannot be generalized into engineering drawings. The first point is, the vision language model is, I think it's quite promising because it achieves the overall, like the highest in endpoint score, and it's not bad, right? And it's only 8 billion parameter, it's not big. And a bit of update with our current work, so we're detecting this, we're doing kind of cross-sheet linking, so we're detecting this kind of, this kind of section marker or elevation marker that appears in a plan or in a specific layout, and this kind of reference symbol, it will point to another layout in another drawing. So yeah, our current focus is basically detecting the layout, and you do some OCR on the symbol, so we will see this is like the layout number 10 from the drawing A301. So we will go to the drawing A01 and link them kind of together, so it's like a more comprehensive understanding of the drawing. It's not just within one drawing sheet, but it's crossing